Hi, my name is McCartney and this is my final video on the counting circuit. It will include a description of how the counting circuit works by breaking down all the components and also some demonstrations. So first off, just starting with the demonstration, if we turn on the circuit with this on-off switch here, the display will light up and show 0 because the count right now is at 0. If I press this button here that starts the count, the counter will start counting up from 0 to 9, and then it will repeat that for as long as an internal clock stays on, which will be explained later. There's also, besides the button and the on-off switch, there's a switch here that adjusts which way the counting circuit counts. So now it's counting down. So starting at the very beginning of the counting circuit, we get to the button input, and the button input is just a button that goes through the NAND gate. So if we press the button, the LED comes on. One thing that I'm going to be trying to do is to use bicolor LEDs whenever possible, because I think that the bicolor LED helps illustrate that there is oscillation happening in a lot of parts of these circuits, because instead of being off half the time, which just indicates that there's no potential voltage, it will change between red and green, which means that current is flowing through, which kind of helps prove, I guess, that when a logic state is 0 with logic chips, it's actually delivering ground. So it goes from green to red when you press this button, instead of just going from green to off. This part of the circuit is where we introduce RC1, which is a resistor-capacitor pair, which are used to customize timing. So we have this RC pair right here with this capacitor and this 1 mega ohm resistor. And in the next circuit, the NAND gate oscillator, we will be adding another RC pair that will control the frequency of the square wave. So here, if we press this button, this RC pair controls how long this bicolor LED stays green. So for example, here I have swapped out the capacitor for a larger one, and now if I press the button, the bicolor LED will stay green for longer. I cut it out, but that was almost 50 seconds. Here is the engine of the whole circuit. It generates something called a square wave that the whole circuit will run off of as a clock cycle. A square wave is like a waveform, except the rising edge and falling edge are almost complete vertical lines, and the negative half and the positive half of the wave are both equal times, or the duty cycle is 50%. So if we press this button, the bicolor LED that I have in starts flashing between red and green. The new chip in this circuit is the 4017 decade counter, and in a minute I'm going to show you how it can be used to make 10 LEDs come on in sequential order, one at a time. But first off, I want to point something out. The only part of this chip that is used throughout the whole circuit is pin 12, so you might want to be paying attention to what pin 12 does. Before, you may have remembered that I mentioned pin 12 and that you might want to pay attention to it. Pin 12 is the divide by 10 pin. The bicolor LED that you can see blinking between red and green in the sequential LED order, that is pin 12. That is the divide by 10 pin. For half the time when the count is between 0 to 4, it will present a low output, and when it is from 5 to 9, it will present a high output. So what this effectively does is it takes the frequency of the clock that is given to pin 15 and divides it by 10. So firstly, before I get into what the new chip right here is doing, I think it's important that I explain what just happened to the 4017 chip, which we were currently using to power 10 LEDs in sequence. So in that circuit, we also had a bicolor LED that was turning on and off depending on what the pin 12 divided by 10 output was. And this blue lead now comes from pin 12 into the clock input of this chip here, which is the 4510. And the 4510 is a BCD counter. So what the 4510 and the 4516 chips do is they're both BCD counters. And what that means is they count in binary coded decimal. Binary coded decimal is like binary, except there's a 4-bit number for every digit in decimal. So for a more in-depth look at BCD, if we take the decimal number 128, which many people realize is 1 with 7 zeros behind it in binary, and we convert it to BCD, we get the nice clean BCD number of 0001, 0010, and 1000, or 1, 2, and then 8, which is 128. So even though I said that both the 4510 and 4516 are BCD counters, they're really just 4-bit binary counters because they only represent 1 digit in decimal, which means they're just 4 binary digits or 4 bits representing 1 decimal digit. The second last part of this circuit, which is the 4511 decoder chip right here, takes the 4 outputs of the 4-bit or nibble number provided by the BCD counter, and it decodes them into 7 outputs, one controlling each segment of the 7-segment display, which we will add in the next step. So the 7 pins on the top here that are not being used will each be connected to one LED section of the 7-segment display, which will control the number. So what this chip does is, say the BCD counter is outputting a 1, the corresponding pins to 1 on this decoder chip will turn their value to high, which will then power the LEDs in the 1 places, so the 2 to the right hand side on the 7-segment display when we add it. So this is the final version of the circuit on the breadboard before we transfer it to the PCB and make it more permanent. So we can turn on the circuit by pressing the button, it will start counting, and then we can flip the switch and it will count the other direction. The second last step in this marathon project is the PCB case. A PCB case is just a PCB or a printed circuit board where you solder in the parts, hopefully on the right side. And once you do that, you get something that looks like this, which is the top of the demonstration you saw at the start of the video. So this is the final product. I'm not going to give another demonstration because there was one at the beginning, but all the pieces soldered onto a PCB in a 3D printed case with the battery inside. So thank you for watching.